So I'm from CartoDB. We're a cloud mapping company. We take people's spatial data and turn them into very, very beautiful maps. You see a lot of our maps in things like newspaper sites. So we can do pretty maps at big, big scale. And underneath our beautiful mapping engine, it turns out, is Postgres and PostGIS. So people sign up for a CartoDB account. They get a beautiful interface to drag their data into. We quietly stuff it into a PostGIS database behind the scenes, and then drive the mapping engine out of that. And because it's in this database, we can do, in addition to drawing beautiful maps, actually all the spatial analysis that PostGIS allows as well. So it's actually quite a powerful platform. Before I start, I'd like to wish you a happy GIS Day. Happy GIS Day. Today is GIS Day. It's a made-up holiday. It's made up by a company called Esri, the Microsoft of the GIS industry. So it's nominally a non-vendor-oriented celebration of all things mapping, the wonders of geospatial analysis. It's a place for GIS techs to get together and tell the public what they do for a living. But the reality is they started the event up kind of after they had attained Microsoft levels of product lock-in. So it's really kind of a great excuse to have people talk about cool things you can do with their software. So generally speaking, I do not celebrate GIS Day. I celebrate the day after GIS Day, which is not today, it's tomorrow. So what would you call the day after GIS Day? PostGIS Day. Of course. So today I'm going to be talking about PostGIS Gotchas. And by and large, using PostGIS is supposed to make working with geospatial data easy, and certainly easier than pulling out a custom GIS desktop solution, something like that, at least for database people. Like you hear today, it's easier. In PostGIS and spatial databases in general, location information, the points, the lines, the polygons, they're just another column in the database table. And because they're just another column in the database, you can reason about them using relational logic. So you can join tables on spatial conditions, you can filter on spatial conditions, like find the 15 nearest coffee shops to your location, that kind of thing. And yet, there are definitely gaps through which people can fall. And all of a sudden, what seemed like a really simple and obvious thing becomes an annoying black box. And a lot of these gaps fall into the category of things that people like me who started in geospatial and then came to databases later take for granted. But they're not immediately obvious to folks who started maybe with databases or programming and are coming later to geospatial. So pitfall number one, projections. And there's a disconcerting number of pitfalls that have to do with projections, either directly or indirectly. As the diagrams show, map projections, they're just mathematical transforms between angular coordinates on a sphere, latitude and longitude, and Cartesian coordinates on a plane. And since the sphere is not isomorphic to the plane, some compromises have to be made when you make those transformations. And at this point, most of you are saying, perhaps with a little bit of righteous indignation in your voice, that it's 2015 by God, and why should you have to model anything on the plane? And I'll give you two answers. So first, it's just history. It's how people have managed cartographic information for 2,000 years. So it's going to take us a little while to change over. And by us, I mean the people who've been producing and managing the data, the people in the counties and cities and states and so on. And second, just ease. It's just way easier to manage data on the plane. You'll note that your web maps, your Googles, your Bings, they're all on a plane. They're on a Mercator projection. And there's a good reason. It's about 10 times easier to reason about things on a plane, as we'll see in more detail in a bit. So this is a polygon. It's a nonagon, in fact, 9 sides. Perhaps it's a really strangely shaped parcel. And you'll note the coordinates along the side look a little funny, maybe. They aren't latitude and longitude, for sure. The nice thing about projections is that they're mostly invertible. So if you know what the projection is, you can take the coordinates from one projection, invert them into latitude, longitude, and then forward project them into other coordinate systems. So the data is really fungible. You're not locked into any one system. And PostGIS is a mechanism for changing projections. Every geometry has an embedded foreign key, the SRID, or spatial reference ID, that you can look up in the spatial refsys table. And the table allows you to convert the numeric SRID into a more verbose projection suitable for driving a reprojection algorithm. So in the case of my demo polygon, my nonagon, the SRID is 3005, which corresponds to a common map projection in British Columbia. And I can look up the projection transformation metadata using that number in the spatial reference system table. And so that's the query that looks it up. And what it looks what it gets back is something that looks like this. So the projection is AEA, which stands for Albers equal area. It's got an origin at 45 degrees north, 126 degrees west, a horizontal offset of 1,000,000 units, and it's all in GRS-80 spheroid. So I can take these fun coordinates and use a reprojection engine with this configuration, and I can convert the coordinates to any other projection I like, which brings me to the next pitfall, which is screwing up your projections. So everything's fine unless the web developer got the data from the province or the county or the state and they uploaded it using the SRID of the projection he wanted instead of the SRID of the projection he had. So if you said use next SRID of say 4326 latitude longitude instead of 3005, and this is a common pitfall, and it's quite hard for folks to back out of once they've made this mistake, because everything seems wrong, everything stops working, but for reasons that are not obvious at all. Because what you get is data in which the metadata, the SRID, doesn't match the data, the coordinates, which means all of a sudden things just stop working. External software trying to draw the data on a map will fail because it won't be able to correctly project things into the display projection. If you work it internally and try to do internal reprojections, that'll also fail because the coordinates don't match the declared projection anymore. So that'd be bad news. Unfortunately, it's not hard to fix. You just have to update the metadata on the geometry objects. And in this case, we alter the column definition to declare the new SRID, 3005, and simultaneously rewrite the geometries to have that SRID embedded in them. Note the function that we use here, st_set_srid. So we're not changing the underlying coordinates. We're just changing the SRID. We're just changing the metadata. So now we have a consistent situation again. And all the transformation math will work. However, if we're real web developers, having the data correctly in the planar projection is no good. We want our data to be in latitude, longitude. And there's two ways of mucking with SRIDs, which are confusingly similar looking. They look almost the same. They both take in a geometry in SRID, and they both return a geometry with an SRID set to the input value. Now the first one, set SRID, which you already saw, it alters the SRID of geometry, but does not alter the coordinates, so it's for metadata management. You add an SRID to a geometry which lacks one, or you fix an incorrect SRID. The second one, st_transform, is the one that people actually want to use. It assumes the SRID on the input geometry is right, and it uses it to transform the coordinates into an SRID provided as a function argument. And here it is in action, changing the projection of an entire column in one go. And again, we alter the column type definition and supply a transformation function to make the data fit the type constraint. But this time, since the coordinates in the SRID match, we can use st_transform function to transform the coordinates into a new projection. And ta-da, we've got geographic coordinates where we're comfortable and everything is easy. At least everything is supposed to be easy until they start to build their app. And the first thing they want to do is to find the distance between objects in their database, where we get to the next pitfall, which is lack of projections. We've just removed all the Cartesian logic from our data by flipping it back into latitude, longitude. So suppose you have LA and Paris in your database in latitude, longitude coordinates, and you want to calculate the distance between them. You'd run the st_distance function, and you get back an answer, 121. What the heck does that mean? Right, it means nothing. The units of the calculation, angular degrees interpreted on a Cartesian plane, they don't mean anything. They don't return anything like a true distance. They don't return an angular distance. There's nothing you can scale linearly to the right answer. So we've gone all the trouble of standardizing our coordinates on an easy coordinate system. And in fact, suddenly things are not very easy at all. So we could put our data into Mercator and run a Cartesian distance. But unfortunately, even though the answer is in meters, we're on a Cartesian plane, it's still wrong, because Mercator isn't a distance preserving projection. It preserves direction, which makes it great for navigation, but poor for measurement. And there is, because the sphere and the plane are not isomorphic, there is no one planar projection we can choose which will make this problem work across the whole wide world. For smaller distances, you can actually stick with Mercator and cadge on a correction factor, 1 over the cosine of the latitude. And that'll remove the distortion, but the correction factor only works at 1 latitude. So it's really only useful if you're doing a local cadge for very small problems, not when you're doing transcontinental problems. What we really want is a representation that doesn't forget that under the covers, we're still living in a spherical world. And if we cast our geometry column into the geography type, voila, then magic occurs. The connections between the points are modeled as great circles. The calculations are done on a spheroid. And the right answer just sort of pops out of the distance area calculations without any hackery at all. Okay, so that was just kind of, that was a long trip. That was a long trip just to find out that dealing with geographic coordinates can be done easily and accurately just by using the geography type. But the geography type itself is another kind of a pitfall. So first is the problem of math. So doing things right on the plane is pretty cheap. This is the distance calculation. It's one of the reasons that local agencies like counties and cities work in planar projections. It's because it's just so mathematically convenient to use a planar model. So it's just one slightly expensive square root call. You can even dispense with that if you're just doing comparison operations. You can just compare square distances as easily as true distances. And remember, historically, we didn't really have a choice of using spherical models in the era of drafting tables and straight rules. And there's no getting around the fact that even something as simple as the shortest distance between 2 points on a sphere requires a lot more math. There's 7 trig calls in there, so you're burning a lot more CPU time to get that one answer. And this is a spherical distance. This is not actually even a spheroidal distance. To do a spheroidal distance in the geography type, it requires the same number of trig functions, but they get called over and over and over again for a converging solution, a Vincenti solution. So it's really, really expensive to get the exact answer on the spheroid. The other reason geography is a bit of a pitfall is there's actually very little direct spheroidal support in PostGIS still. The type and indexes are there. The basic functions went in for version 1.5. The planner got improved for version 2. There's some performance improvements in version 2.1, but there's still really only a handful of functions implemented natively on the spheroid. In terms of algorithms, it's really just distance, azimuth, and projection, which get used in a bunch of functions, and then area. Distance you can actually use for a lot of things. A lot of these guys are just shims around distance. No, intersects and covers are just using a distance algorithm underneath the hood. There's no constructive geometry functions. There is, if you look in the documentation, you say, hey, look, there's a ST buffer of geography function. What are you talking about? It's a trap. Implementing constructive geometry on the sphere is a problem that a lot of spatial databases dodge in different ways. SQL Server dodges it by doing a very low-level planar reprojection in their core geometry library, kind of intersect an edge at a time. They put everything on a plane and then do the constructive geometry. And that'd be cool, but our engine doesn't do that. We did a much more frightening hack. Kind of the same thing, but a higher level, more disgusting implementation. So the geography buffer function starts with the input, which is geography, and casts it immediately to geometry. Then it transforms that to a good planar projection for some definition of good using the best SRID function. Then it buffers that, so now we've got a buffer. Then it transforms that back to latitude, longitude, because that's where we want to be, and finally casts it back to geography. So, as you can imagine, that leads to perfect results every time. No, there's lots of places this can fail. Any overly large object won't find a good projection, so the work will be done in the default Mercator. If you buffer things in planar space, they aren't exactly the same size as the real world. So if you do comparisons between your buffers and the exact calculations of things like the area function, you get back different answers. Everything should be pi r squared in its area, but you'll find that the buffers are not exactly pi r squared because they've been calculated on slightly different projections. So they can vary a little bit. And the whole hack leans rather heavily on this idea of a best spatial reference system. And there's no one best thing for all cases. It does its best to choose the best one given the inputs. So for tiny objects, it'll use uniform transverse Mercator projections. For bigger ones, it'll use Lambert equal area. For polar stuff, it uses polar stereographics. And if it can't fit them into any of those things, it falls back to Mercator. So it's not ideal. There's actually 2 variants of the function, because a lot of times we need the best projection for a pair of objects if we're taking a difference or something like that. So, but that's not so bad, actually, because for most functions in the PostGIS world, there's about 300 of them. And for most of those functions, the difference between geometry and geography is moot, because the functions don't care about the edge interpretations. They just care about the structure. So anything dealing with structural representations, like converting from JSON or XML or extracting pieces of the object, it works just fine. So you want the first point of a geography. It's the same as the first point of a geometry. And it kind of seemed duplicative to go and redeclare all those functions for the geography type, so we didn't. We just left it there and said, you know, if you want to do that, just cast it, or if that really bothers you, just define a wrapper function that does the casting for you. So geodetic reasoning, the next pitfall, is kind of similar to projections. It's my favorite pitfall. I get a ticket like this, or about something like this, about once a month in our ticket tracker or on Stack Exchange. And the complaint is always like, there's something broken in the PostGIS geography code. Because it says that these two objects, which clearly intersect, don't intersect. Now, why would PostGIS think those things don't intersect? And this picture is from PostGIS ticket number 3357 from November 1st. So what's wrong with the PostGIS geography code? What massive error have I made? The problem is not with the geography code, it's not with the algorithm. The problem is with the picture. The picture is broken. It's the picture that he got from his flat map. It's the picture he had in his head when he looked at his line that was straight in latitude and said, oh, it's a straight line. In the spherical world, the shortest path between 2 points at the same latitude does not follow the latitude line, right? It goes, if you're in the northern hemisphere, it goes a little bit above it. If you're in the southern hemisphere, it goes a little bit below it. Only on the equator is it exactly the same as the latitude line. So there's two ways to fix this problem. You can fix the picture, like I did just now, so it displays the geographic situation correctly, or you can fix the object so it reflects your biases. So to fix the picture, to get out a geometry that you can draw on a flat map that still describes the geographic curvature of the object, you just add a bunch of points along that curvature. So for this example, I segmentized the geography. And note that it's important that I segmentize the geography. There's two versions of segmentize. One takes in a geography, and it segmentizes it in geographic space along the great circle arcs. The other one takes in a geometry, and it segmentizes it in Cartesian space along what we consider the straight line. So you can segmentize it and then display it on Google Earth, and it'll go flat, and ask questions of the geography module, and it will tell you that those things intersect because you've forced them to intersect. So this is another one actually showed up on Stack Exchange a couple months ago. It's not quite so nicely worded, but why does the extent of the transform geometry not equal the transform of the extent of the geometry? You know, it's just these things should be commutative. So the user took a box. I think it was a web map extent. They drew a box on their web map, and they found it captured a different amount of data depending on what projection they used it in. So what usually happens is people draw a box in Geographics or in Mercator. You usually use a web mapping tool, and it's a perfect box, as far as I can tell, in the source coordinate system. So the extent of the box is just the box. Then they transform the box to a new coordinate system. And it's still a box, right? It's still four corners. But there's no guarantee that the coordinate grid of the new system is aligned with the grid of the original, which means the extent of the transformed box is not the extent of the original. So it really comes down to the fact that it's not a box being transformed so much as it's 4 points. And when they land in the new system, there's no guarantee those points will still form horizontal and vertical edges. OK, so I probably mined this seam of content down to the bedrock. So here's a use case you have either heard of or solved for yourself. It's the pitfall of unpredictable performance. And this problem seems to be one that comes up over and over again from folks in the startup community, Silicon Valley world. And in fact, in 2009, a colleague of mine solved this problem 3 times in 3 different languages for a succession of startups. So I want to reverse geocode 1,000 points per second. So let's unpack this use case a bit. First, reverse geocode is a term of art, which effectively means if you're given a point, tell me what polygon the point is in. And the polygons can be things like counties or cities or neighborhoods or geofences or really any delineated area. And the source of the points for this problem breaks down into 2 fairly different solution spaces. One source is like a real-time stream requiring a real-time response. So for each point, you want to reverse geocode it immediately, as fast as you can. The other source would be a static collection of points. And PostGIS can address both these cases, but it's very good at one and not so good at the other. So the real-time query looks like this. You create a point literal, and then you find the polygon containing it, and you search the set of, searching the set of polygons can be pretty efficient with the R-tree index, but once you have the set of candidate polygons, you have to blast through every edge in every polygon once to carry out the exact point and polygon test. So the upper limit of speed is kind of conditioned on how complex your polygons are. So if they've got a lot of edges, your calculation is going to be relatively slow and CPU bound. And if they have only a few edges, it'll be relatively fast. Where are we? There. PostGIS can actually answer the point and polygon batch problem a lot faster than it can do the real-time problem, because it leverages the nested loop pattern the query is usually evaluated with. So each time this st-intersects function is evaluated, it checks a statement level cache to see if either of the arguments are the same as the last evaluation. This is basically a spatial join. It's putting the two tables together based on a common location rather than a common key. And the caching trick improves performance for joins where you have moderately complex polygons. It improves the performance by like a factor of 10. But it doesn't help the real-time problem because there's no chance to cache a polygon in memory because you're only doing them one at a time. As we iterate through this join, the index is pulling up one polygon, then pulling up a succession of points and saying, you're in it, 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 you're in it. So you can hold this polygon and have the structure of the polygon cached and indexed. So the two cases have quite different performance characteristics, which is a bit of a pitfall. Streaming processing is slower and batch processing is faster. The streaming solution that my friend wrote 3 times in Scala and C++ and Python, what you do is you just hold the entire polygon set in memory and you pre-index all the edges in the set. And then you can blast through the points in log n time. Basically, you can get the polygon of interest in log n time out of a larger R tree, and then you go through a smaller R tree of the edges of that polygon again in log n time. There are streaming reverse geocoders, one called Two Fishes, which was built by Twitter or Foursquare. Anyways, it'll happily streaming geocode millions of streaming points. And that's what they do. They just hold the data in memory, all indexed, all pre-indexed. Okay, another pitfall, the mysterious operators. So this is something that only an audience of Postgres nerds would notice, but I've showed a number of cases of bits of SQL so far, and we tend to hide our operators. You haven't seen any operators yet. You've seen where clauses, you've seen functions, and I've talked a little bit about using indexes, but there have been no operators in my SQL so far, so what gives? The answer is we hide our operators so that our SQL can look like the spatial SQL which is specified in the Open Geospatial Consortium standard for spatial databases. And one of the things they specify is that you should be able to use an st-intersects function, a spatial predicate like st-intersects, without having to have any extra magic. st-intersects will do exactly what you want, and hopefully it'll do it really fast. So we wanted that nice simple function to be fast, so we inlined an operator call into the SQL function wrapper, which you can see right here in the green. And you can see the operator in there, our favorite operator. It's the ampersand operator, which means overlaps. Actually, it means bounding boxes overlap. The ampersand operator also means overlaps for geography as well as geometry, and for the built-in range type in Postgres. So there's a bit of a congruence there in meaning, which is nice. We've got a lot of other operators too, but 95% of the functions you might use rely on just really simple box overlaps relationships as a primary filter. And it's worth noting that we only use ampersand as a primary box filter. We count on the other functions to do the work of winnowing the result down to a final set. So I don't know, if we were writing PostGIS now in the present rather than in the past, 10 years ago, we'd probably have made the operators exact and use the internal recheck mechanisms so that we could apply exact tests on them. But at this point, lots of third-party code expects the behavior we have, which is just a high-performance bounding box only filter. So here's what all our operators are. There's lots and lots of them. And you can notice that even though the op class type is geometry, the operators, they actually only do bounding box ops. They don't do exact geometry tests. So the containment operator does box containment. Over left, over right, left, right, they're all just about the bounding boxes of the objects. Probably, again, if we're doing this in the present, we'd probably strip it down to just overlaps and containment. But this, again, is a source of history. 10 years ago, we looked at the example implementation in Postgres and just copied it. Oh, we'll do all this, over left, over right, No one uses overleft or overwrite, but there they are. So another gotcha note. So our spatial index is an R tree. It's built on the GIST API, the generalized search tree API. But it's not the only geometry op class in PostGIS. There's another op class. There is a btree. Oops, where'd it go? There's a btree op class too. There it is, right at the bottom. So why do we have a btree op class? There's a couple features in PostgreSQL, group by, order by. They don't work unless you have a btree op class. So we had to build one if people wanted to, and they did, want to group and sort based on their geometry columns. It's mostly a bad idea to do that for reasons which will shortly become clear. But this dual op class situation leads to a couple of potential gotchas. The first gotcha is the syntactical gotcha. So there's an obvious and easy thing to do. Create index on my table, geometry column. Of course, right? That's an ordinary create index call. And it'll work, even worse. It'll work. There'll be no error returned. But it's going to build you a btree index. It won't build you a spatial index. So then you'll run your spatial queries and you'll say, why is this still slow? I built an index on it. It's got an index it can't do anything with. So what you really want if you want a spatial index is this. It's exactly the same syntax, except it's got using gist in there. There is only one geometry op class for gist, so it'll pick the default op class and it'll all work magically if you say using gist. So the second btree gotcha is the ordering I mentioned. So the way ordering works in the btree op class is completely brain dead. It does provide an ordering, but it's a brain dead ordering. Order by on geometry results in an ordering, but not a great one. It uses mostly the xmin value. So mostly you get stuff sorted on their minimum x value, except when things tie, in which case you go to the y or the z. So you work your way through the box, resolving all the ties. And if you can see, if you use these conditions, sort on x unless there's a tie, then on y unless there's a tie, then on x max if there's a tie, then if all those things go through, then you have equality, which means if you do a group by, looking for things which are equal, your groups are going to be grouped on bounding box equality. So there's a pitfall. Two things can be different and yet share the same bounding box. Also not nice. So watch out. Again, a piece of history. In terms of other indexes, it's worth actually showing. We can do a bunch of different other index creations you might use in PostGIS, though less frequently than sort of standard flat 2D indexes. So this is your standard two-dimensional spatial index. Just create the index in the geometry column using GIST. PostGIS also supports multi-dimensional indexes, taking into account little things like 3D data or spatial temporal data, X, Y, Z, T. So you can get a multi-dimensional index. So you can do it's exactly the same, except you specify a different op class. You want to use the GIST geometry ops ND, so it's a little tricky. Once you have that index, if you want to actually do multi-dimensional filtering, you end up using a different operator, the triple ampersand, because you can never have too many ampersands. We just tack an extra L on to count for the extra dimension. And then finally, if you're using geographies, again, the index looks just like the geometry index, except you use a geography column. The default op class will pick up the right functions, and you'll get a nice, clean geodetic index on your geography type. So another pitfall, mysterious emptiness. So changing track. This is a pitfall very specific to spatial. At least it's specific to this. It's a subtlety of spatial reasoning. It's worthwhile to surface. So getting all philosophical. What is the intersection of a pair of disjoint objects? Is it the sound of one hand clapping, right? Is the sound of a tree falling in an empty forest? The answer to ST intersection of A and B, where A and B are disjoint, is empty. It's an empty geometry. It's a geometry that represents the presence of nothing. This is a concept that folks can find hard to grasp sometimes, particularly in the database world, because it feels duplicative. Because we already have something to stand in for nothing. We have null. But empty geometry is not null. It has quite different semantics, specific semantics. The best analog for empty is 0, right? There's no magnitude, but there's something there, right? And you can kind of see it with an example. Suppose we want to union the intersection of A and B with the third object, C. So the intersection of, if the intersection of A and B returned null, then the union of C and null would, standard database logic, be null. null in any operation also returns null. Doesn't matter what the other operand is. And that's not the right answer. If the intersection of A and B is nothing, the union of C with nothing is C. C comes through. So if you have the concept of empty, it all works. A and B return empty. The union of a geometry with empty is the geometry. C comes back. It's the same way that the sum of 10 and 0 is 10. So having an empty placeholder makes spatial logic work right. Coming up with an empty geometry is somewhat rare, but it's not unheard of. Off the top of my head, there's 3 ways to come up with an empty result, which aren't that infrequent when you're mixing objects of different size in different spatial operations. So there's one we saw, the intersection of disjoint objects. If you run a geometry simplification, but use a tolerance larger than the object, that can just make the whole object disappear. If you run a negative buffer on an object using a radius larger than the object itself, you can shrink it down until it just disappears. Or if you difference a large object from a smaller object that's inside it. So subtract a big thing from a small thing, there's nothing left. So you can get geometry empties, and it's not that uncommon if you're doing actual spatial processing. Another pitfall, more unpredictable performance. So this is a GIS question. You can tell it's a GIS question because the point of reference is ArcGIS. Acquiring ArcGIS-like speed in PostGIS. So Esri, who makes ArcGIS, they've been around for 30 years. They've had lots of time to optimize common spatial ops. The ops this question is about is an overlay operation. So basically an overlay takes in 2 spatial tables as input, and it outputs all the places the tables interact, merging the attributes from each one into the new result. So every boundary that exists in the 2 inputs exists in the output, and all the shapes get a little bit smaller. So the naive way to do this is the way that the questioner tried and found a bit too slow, is this one. You find all the cases where we have a true condition for intersects, then we perform an intersection on just those cases. That way we minimize our calls to this constructive function, intersection, because constructive functions are always fairly expensive. And for a simple case, that works fine. The intersects predicate ensures we only take an intersection of objects that interact. We don't waste any cycles there. But the questioner actually had a data set more like this. Can you see the boundaries? Yeah, good. This is kind of the more common case you'd see for an intersection overlay, where one of the layers is quite detailed and the other one's quite large, because the reason you're doing this operation is for summaries. You want to find out how much of A is inside various categories of B. And then for the A's that cross the boundaries of B's, you want to cut them and prorate them on either side of the object. So the intersecting here is done so that values in the borders can be prorated. And the thing to note is that most of the small blue polygons that intersect the hexagon, they fall 100% inside. So you don't have to cut them. So there's an opportunity for an optimization here. And this is what made things way faster. This is what that's why I've got 60 points on Stack Exchange for this solution. We still use SD-intersects. It winnows things down to just the overlap cases. But in addition, we avoid running that intersection case, that intersection function, in cases where the objects are fully contained. So the questioner for his data, he said, whoa, that's way better. It's 20 times faster. And the reason it's 20 times faster, like I talked earlier about the caching behavior PostGIS uses for spatial predicates for the true-false functions, where the last used polygon is indexed and cached and held, and this comes into play again here. The intersection function, the constructive geometry, doesn't have any caching behavior. So it doesn't gain any efficiency when arguments are repeated, but the contains function does have caching behavior, and so does the intersects function. So guarding calls to the uncached function with the cached version makes things, well, in this case, 20 times faster. It's entirely a function of how complex the larger polygon is. So the caching code, which I've been talking about, is referred to as prepared geometry. It's kind of like, looks like a prepared statement. A prepared geometry is optimized in advance, then kept around and reused. So it's available, and it's available only in these 5 functions. And you'll probably use the SD-intersects variety most frequently. And there's actually inside, if you go into the code, there's 2 different caching code lines, and one only comes into play for point and polygon cases. And that code line is 100% native to PostGIS, and it's about 50% faster. And then there's a generic code line, which uses the GeoS library implementation of prepared geometry. So another pitfall, one problem, many solutions. One last pitfall. It's quite a common one. It's more common for GIS people to fall into than database people. There's a really common spatial query pattern kind of a use case question. It's find me all the objects A within a radius, within a set radius of this object B or these objects B. So, you know, find me all the coffee shops within 500 meters, or notify all the households within a 200-meter buffer of the construction zone. And how the user interprets the word problem, how they interpret the within a radius or within a buffer part of the question can lead to quite different constructions when they're building their spatial SQL. So these are 3 spatial joins. They all answer that same question that associate records in table A that are within 500 meters of records in table B. And all these constructions return the exact same result set, but with very different performance characteristics. So the first one will use a spatial index, because it's got st-intersects running in there. But before it gets to do that, it's going to have to buffer every geometry in table B. And there's nothing more expensive in the world of PostGIS than functions that build new geometry as outputs. Buffer is an expensive function, so it's a loser. The second case uses a much more efficient function. It uses st-distance, very quick, no constructive geometry to calculate a parameter, but there's no spatial index in play. So the query ends up building a full Cartesian join, and then it whittles things down using the actual distance. Only the last option, only the std within option performs well, because it combines an embedded spatial index with a cheap distance filter. And you can see why if you unwrap std within. A surprising number of functions are actually wrappers on top of the actual magic. So if you unwrap std within under the covers, the trick's fairly obvious. We create an expanded bounding box for each side of the query. And the bounding box has the radius inscribed in it, so everything in the box will also be in the radius. And then we let the planner figure out which use of the operator is most efficient. So it'll figure out which side is most efficient and execute it in that way. And then we got the circular radius, the actual std within exact calculation is performed once the index has done its magic. And actually that final test, the std within function, is itself somewhat optimized for the fact that it's doing a radius test. As soon as it hits the minimum distance, it stops, because it knows true or false that it's hit it. So it short circuits and makes things even faster. Another pitfall is Raster Disaster. I don't know if you guys will get sucked in by it, but there's a lot of people who have raster. They're actually people with imagery, and they have this serious misapprehension which has been stoked by database vendors in the GIS world that putting raster imagery in a database is better for various values of the word better. Because everything's better in a database. So they take their files and they stuff them in. I think originally there might have been some utility for this in the ArcGIS ecosystem, and it allowed the vendors to sell server software, so they were really happy with it regardless of the efficiency characteristics. Oracle came late to this game, and they're happy to tell you, oh yeah, put your imagery in the database. But most of what people are doing, they're stuffing it in, and then they rip it back out and stick it on the screen, which is it's a total waste of time. They should have just left it in their beautiful imagery files that are already optimized for access. But the database vendors have an interest in not being efficient about these things because they can sell more software. You don't want to use it for stupid imagery storage because it wasn't built for that. So for PostGIS raster, you really want to use it for analysis. Because everything, when you load the rasters up, you're not getting this sort of magic under the covers thing, which is incredibly efficient. All we're doing is taking the rasters and chopping them into tiny little squares. And then we store those tiny little squares in the database. And that makes them useful for things like raster vector analysis. So I did this little analysis when I first got my hands on raster. I grew up in the center of British Columbia, lots of logging there. So I pulled a whole bunch of logging polygons out, and I compared them to the digital elevation model, the slope and aspect, to calculate which polygons were on steep slopes. Because if you do a clear cut on steep slopes, basically you're ruining the forest. Because when the rain comes down, the topsoil is going to come off, and you'll be left with a pile of gravel. So it was a nice way of seeing where the logging was good and where it was bad. And you can do this lovely cojoint raster vector analysis, and that was a good use of raster. Stuffing your imagery into the database so you can pull it out again to look at it is not a good use of raster. So another pitfall is hidden features. What do we got here? Oh yes, right. So a lot of the stuff I've shown with respect to st-intersects, intersections, so on, all those algorithms are actually driven by a geometric library that's not part of PostGIS. It's used by a bunch of software in the open source geospatial world called GEOS, the geometry engine open source. But that is not the only geometry engine we have available to us these days. As of PostGIS 2.1, you can actually swap back-end engines and use, alternatively, the Seagull engine. via the SF Seagull wrapper library. Seagull is more of an academic library, the computational geometry algorithms library. They have not everything that GEOS does, so they can't actually provide full coverage for every function. So when you turn on SF Seagull, you still end up with a lot of functions served by GEOS. GEOS is the default engine. But Seagull does provide a bunch of functions which GEOS doesn't. A bunch of 3D stuff, 3D intersection, tessellations, volumetric ops, cool stuff like medial axes and things like that. But it's not immediately obvious. You read the docs and you say, oh, look at this, I want to do a medial axis. And it says, no, I don't know anything about that. Well, it's two things. A, you might not have compiled it. Or it might not have been built by your packagers. You'd be completely out of luck. But even if they did build it for you, it's not going to exist until you turn it on. It's not part of the default extension. Raster is part of the default extension. All the GEOS engine stuff is part of the default extension. But you can't use the Seagull engine until you turn on the PostGIS SF Seagull extension. And that's true, actually, of a few other hidden features in PostGIS. We do have a geocoder. If you're here for the last talk, he talked about geocoding. You can geocode directly inside the database, at least for the continental US, using the Tiger data set. And it's way faster than doing HTTP calls, but it only works for the States. There's also a topology extension that lets you do planar topology, so you can model structures where the shared edges are not duplicated. So it's useful for things like census data, parcel data, things where there's only one edge bounding areas. And this is not true, but probably in the next release it will be true. We're going to abstract the raster stuff out so that you no longer get raster by default, but you have to turn it on. It'll allow us to build slightly lighter packages for people who don't want raster. And beyond PostGIS, there's actually even more hidden features. If you're doing geospatial, and I bring them up just in case you're interested, if you're doing LiDAR work or if you have really large, multi-billion collection of points, you might find that using something which is optimized for storing large collections of points makes things faster. So the point cloud extension is for folks with LiDAR data. And for folks doing routing logistics, the PG routing module actually has, in the open source world, probably the most complete set of routing implementations. So they don't just have sort of your naive Dijkstra stuff. They've got A-star and shooting star and C-star routing algorithms. They also do some traveling salesman solutions as well. So it's all pretty cool stuff. So those are two sort of hidden features you might not have known about in the PostGIS ecosystem. So that's been a limited tour of the oddities of the world of PostGIS and geospatial. Some of the pitfalls have to do with spatial reasoning. A lot of them have to do with historical legacy. Like everyone, I feel sort of a combined pride and disgust at the code base that I manage. But that's what happens when you have a 10-year-old code base. But they all have all the limitations have one thing in common, that they're really confusing and frustrating the first time you run into them. And hopefully this will help you avoid running into them. So this would be a great time for questions, or if you've had your own pitfalls which you want to talk about, let's hear from you. Pitfalls, questions?
I'm actually really
Yeah.
curious about what the most expensive query you've ever seen, and in terms of how easy is it to time out a query? What's the most expensive thing that you've seen this library do?
Well, actually, those overlays tend to be the ones that people start off really long processes and go, Some of them are some of the most expensive things are things which are done by poorly putting together the functions and building up terrible situations. But in terms of sort of well-optimized queries that still take a heck of a long time, the overlays probably are the most frequent one. Yeah. Yeah.
Are you familiar with GeoDjango?
Yep. Well, no, but I know it exists. I know it's cool. I know it runs on top of PostGIS. And I think I met the creator once. But
You know that it's like an ORM for GIS.
yeah.
For PostGIS.
Yeah.
So I wonder how easy it is to shoot yourself in the foot when using GeoDjango. Because with the ORM, people write
Yeah.
queries.
I think I don't know enough about it to know for sure. But a lot of these ones, when I look at the example code, they've done a reasonable job of blocking out sort of the 80-20 cases. Oh, you want to do search within a radius. OK, here's a simple pattern to do that. You want to find things within this. OK, here's a simple pattern to do that. And the ORM, of course, will happily do exactly the right thing. But so much of spatial queries involve stuff which you wouldn't want to have an ORM synthesize for you. That I think a lot of the time they just say, you know, go ahead and write your own custom SQL inside and wrap that. All right, thanks a lot, folks.